So the sine rule is an important application in trigonometry. It sort of, again, sort of forms an extension to the Pythagoras theorem. So we've already looked at the Pythagoras theorem. That's sort of the first thing you learn when we look at right angle triangles. That forms the basis. And then we look at our trigonometric ratios, right? So then you are introduced to your sine ratio, your cos ratio, and your tan ratio. Now this sine rule is an application of course the sine ratio in itself. And again, what it's giving us more opportunities depending on the information that we're given to find out more about triangles. And now this actually allows us to expand into non-right angle triangles as well. So we can start looking at our other types of triangles, and using these trigonometric ratios, we can find unknown lengths and sides of and unknown lengths and angles of triangles that don't necessarily have to have a right angle. So if you look at the sine rule, it basically says that A over sine A is equal to B over sine B is equal to C over sine C. Now what that means is, say you have sine of an angle, the lowercase a and the upper capital case A, that basically refers to an angle and its opposite side. So I'll show you what that means when we go through some examples. But it's basically saying that a side or sine of an angle over its opposite side is equal to sine of another angle over that angle's opposite side. Okay, and you can have sine at the bottom or the top depending on whether you we're required to find a length or whether you're required to find an angle. There. So we'll just go through an example here. So you can sort of understand what I mean. So over here it says to find the missing angles in these triangles. Okay, so then we're going to be using the application of the sine rule. And what it is we're looking at, we're wanting to find this angle, right? So what I'm going to say is that sine of this angle over its opposite side, okay, is equal to sine of this angle, because that's the other angle we have, over that angle's opposite side. And you can see I've written that here. So that means that sine theta over 2 is equal to sine 53.2 degrees over 4.9. Okay, so this angle over its opposite side is equal to this angle over its opposite side. And then we're basically just rearranging this to find theta by itself. So you multiply both sides by 2 to get sine theta by itself, and then to get theta by itself, just to get the angle, we take the inverse of sine and put this in your calculator. Now again, notice how I've spoken about this before as well, that we're not actually rounding our answer until we get to this last step. Because if you round our answer here, then we're going to put in a different number into this answer, and our answer here could be different. You know, it would end up being 20 degrees or 18 degrees or something like that, which could be incorrect. Okay, similar thing for here, except we're just looking at this outer angle here, so nothing to be confused about. We're just going to look at this angle first, okay? And I've just said that theta is equal to 180 minus this angle, which is GIH. So if we try to find this angle first, so then sine GIH over its opposite side, which is 0.5, is equal to sine 135 over its opposite side, which is 0.9. And then we're doing the same thing. So angle GIH is equal to this sine inverse, all of this expression here. And then obviously we want to find theta, which is 180 minus this angle. So we just do 180 minus all of this. And that gives us 156.87 degrees. Which sounds about right, because we know that this is an obtuse angle. And the reason we do 180 is because this whole thing is a straight line. So whatever this angle is, the theta is going to be 180 minus that angle. Okay, pretty straightforward stuff. Next question again, same application of sine rule. Here we're just looking at finding sides instead of the angles. Now what we need is we want to find if we want to find the length of this side, we need to have the opposite angle, right? Which we don't currently have. But using our angle sum over triangle, we can figure that angle. We can figure what this angle size would be, because we know what these other two angles are. This is 29 and this is 77. And you know that the three angles in a triangle, they have to add up to 180. So therefore, angle ABC is equal to 180 minus 77 minus 29, which is equal to 74 degrees. And then we can do our calculations. Now, because we want to find a side, we put the sides or the length of the sides of the numerator and the angles on the denominator. Okay, so if you're finding angles, you put the angles on the numerator. If you want to find the side and unknown side, then you put the sides on the numerator. So this will be x over the opposite angle, which is sine 74, what we've found here, over, we'll pick this angle because we don't know what this side would be. So we're going to pick this angle because we have its opposite side as well. So over sine 87 over sine 77. Okay, so then x is just equal to 87 times sine 74 over sine 77, which is equal to 85.83 centimeters, correct, 2 decimal places. Okay, this one again, pretty similar. We already have all the angles and all the sides that we need, so we don't need to do any calculation like we did over here. So again, x over sine 40 is equal to 6 over sine 49. And x is just equal to this, which gives us 5.11 millimeters, again turned to 2 decimal places. Okay. Yep, now the last question, bit of a multi-stop question here, but again, they've given us the diagram, so that makes things a lot easier for us. So BC is equal to 10 centimeters, angle ACD is equal to 77 degrees, angle BDC is equal to 26 degrees, DAC is equal to 40 degrees, and we want to find the length of BD first. So I'm just going to highlight that just so we know what we're talking about. So if we want to find the length of this side first, okay? So which application would we use? Again, we're going to use the sine rule here. So we know that 10 over sine 26, these are opposite angles and sides, will be equal to BD over sine 77. So BD is equal to 10 times sine 77. Yeah, so we're just multiplying both these sides by sine 77. So BD is equal to 10 times sine 77 over sine 26, which gives us 22.23 centimeters. Okay. Now I have rounded the answer because this is a separate question in itself. But if we require to use BD for the other questions for B and C, I'm still going to be using this answer, not the rounded answer. So now we want to find the size of angle ABD. So ABD is this part here, this angle here. So we just note that down again, just so you guys know what we're talking about. ABD is here. And to do that, so we know what x, no, we don't know what x is, sorry. So we have this length, this angle on this side, and then we would need to know, oh yeah. So this does actually require any sine rule calculation. Sorry, I was getting confused here. So what we're going to use the angle sum or triangle. So if this is 26 and this is 77, we know that this will be 180 minus 77 minus 26. Again, using the angle sum or triangle. Okay, so that gives us 77 degrees. And then because this forms a straight line, that means that this is going to be 180 minus 77, which is 103 degrees. So apologies for that. So there's no sine rule required for that question. But we will be requiring this solution to find the length of 80 now, which is marked as x here. So again, let me just highlight that for you guys. ABT here. Okay, so that's the length we're finding now, marked by x. So now we know what this angle is. So we can use this angle over this angle. Sorry, this angle over this side, or this side over this angle is going to equal this side over this angle. Okay, so we already know what BD is, so we can write BD over sine 40 is equal to x over sine 103. Okay, that's what we found in our previous answers, right? BD we found in part A, and sine 103 we found in part B. Okay, so x is equal to sine 103 times BD over sine 40. So what you can see is by BD here, I'm using this exact solution. I'm not using the rounded solution when I'm solving that. So put that all in your calculator. If you put, if you put this in your calculator first, save that in your calculator storage, and then do sine 103 times that over sine 40, you will get 33.69 centimeters, correct to 2 decimal places for that one. Okay, so that's some application of the sine rule there. We can see how we're building on. So we started off with the right angle triangles, and using Pythagoras theorem. Then we built on that using trigonometric ratios to find unknown sides and angles. With less information. And now we're building on that more by using something like the sine rule, which can help us find unknown sides and angles in non-right angle triangles as well.